Okay, so as mentioned before, I was going to go over section 9.3 and 10.4, the confidence interval for a population standard deviation, and the hypothesis testing on a standard deviation. So this was not covered in the previous stats course. The reason being is because they they just ran out of time, and we just don't have enough time to go over this information, and the reason that it's kind of complicated and we don't want to go over this information in 243 is because it introduces a new type of distribution known as a chi-squared distribution. And it was just enough in 243 to just go over the z and t distribution, and we felt like it was unnecessary to bring in the chi-squared distribution. It would just be a little too confusing, but really it's not that confusing. And so I'm going to introduce this to you now, the chi-squared distribution. So the chi-squared distribution, and chi is a Greek letter, and looks like that, and squared, so squared, chi-squared distribution. So the chi-squared distribution, and so the way of thinking of this in terms of the standard deviation and what values we'll be dealing with, if a simple random sample of size n is obtained from a normally distributed population with mean mu and standard deviation sigma, and so for confidence interval for sigma, sigma will be unknown. Anyways, population with mean mu and standard deviation sigma, then chi-squared is equivalent to n minus 1 s squared divide sigma squared. And so this has a chi-squared distribution with n minus 1 degrees of freedom. So we're going to be dealing with degrees of freedom again, like t distribution. And so in this case, we're going to be dealing with this equation right here. So it's pretty straightforward, the equation. It's not too bad. It's going to be more difficult this term because you're not familiar with it yet, but you will be familiar with it. And we'll actually notice that this is a distribution unlike T and Z distribution. T and Z distribution, they were both centered at 0. They were both symmetric. They were different shapes, Z and T, but they both had those characteristics, and more other characteristics too. But the shape of a chi-square distribution is not normal. It's not symmetric at all. And we'll actually see as if you increase n, it'll get closer and closer to a normal distribution, but it's not a normal distribution at all, especially for large n or small n. Like the t distribution, the shape of the chi distribution depends on the degrees of freedom. So you can find an illustration of this in the book. I'm not going to go over that too much, but yeah, just go ahead and look at pictures in the book. As the number of degrees of freedom increases, the chi-squared distribution becomes more nearly symmetric, as I mentioned. And the values of chi-squared are non-negative. So you'll only obtain positive values. And that makes sense. If you look at this equation, n minus 1, that's always positive. S squared, that's always positive. Anything squared is positive. And similar, this is always positive. So chi-squared is always positive since we're taking the product of two positive numbers and then dividing by a positive number. So strictly positive. And so if we think about what's going on here, well, actually, we'll get to that in a second. So we're going to be using this equation to estimate what sigma is, or sigma squared, the population variance. but we'll just stick with standard deviation. And so let's go ahead and solve for sigma squared with this equation. There's our first step. And then, so we have sigma squared times chi squared equals n minus 1 times sigma squared. And lastly, we would divide by chi squared. And we would obtain sigma squared equals n minus 1 times sigma squared, or s squared times chi squared. And actually, lastly, we would just divide by sigma, or not divide by sigma, take the square root of both sides. So we would just obtain sigma equals the square root of n minus 1 times sigma squared over chi squared. So we can solve. We've solved for sigma, and we're going to use this information to derive a confidence interval for sigma. So to do this, we'll have to solve for some chi squared values. And to do this, we would have to know how to read a chi squared table. So one piece of information when reading a chi squared table, I'm going to write this on the top of the next page, our equation here. So we're going to be dealing with this equation. So it's very similar to a t-distribution because the left side of the column is the degrees of freedom. So we take n minus 1, and that will tell us which row to look at. So that will give us the row. And then the part that's much different that you really need to keep into consideration is the area to the right of the critical value. So, so for example, let's just look at a chi-squared distribution. It's kind of shaped like that. Actually goes down to 0. And for example, if the tail here, if the area on this tail is 0.05, then the chi-squared value right here would be 0.95 because the chi-squared value that we're looking for from the chart is actually the area to the right of the given value. So 0.95 is the area to the right if the area on the tail is 0.05. So we would look at the column with 0.95 representing the area to the right to obtain this value. So for this example, let's consider that we are looking at a degrees of freedom of 15. So let's imagine we have n equals 16. Then df equals n minus 1, which is 15. So we would look at row 15, and we would be looking at, to find this chi-squared value, we would be looking for 0.95. So we would look at column 0.95 and look at that intersection, and that value would be your chi-squared value. And if you read, looking at the chart, we would see that 15 intersect with 0.95 column would be 7.261. Now, similarly, let's try to, since we're doing a confidence interval, it's the same idea. We want, for this example, since we're looking at a one tail equal to 0.05 and another tail equal the same, 0.05, then this chi-squared value would be subscript 0.05 because it's the area to the right, in this case 0.05. So this would represent a 90% confidence interval. Okay, so this would be because 0.05 plus 0.05 is 0.1, so the middle area is 90%. 90% confidence interval. And we would look up 15 for this value right here, and 0.05, we would see we would have 24.996. Okay, so those would be those two values would be your critical critical values, which you would use to determine your confidence interval for sigma. So let's just look at an example to see how this has worked out completely from A to Z. So let's look at problem let's just look at problem 10A on section 9.3. So a simple random sample of size n is drawn from a population that is known to be normally distributed. It must be normally distributed if we're going to be using a chi-squared. It's mentioned in the definition. So we're good with that. The sample variance, which is s squared, so we're looking at 10A from section 9.3. So we're given that s squared is equal to 19.8, the sample variance. Okay, so that's 19.8. And then on top of that, we look at part A, and we see that we're going to construct a 95% confidence interval for sigma squared. So 95% confidence interval, if you think about it, draw a picture if you need to. I'll go ahead and do that so you can visualize it. So, well, actually, I'm going to redo this. We're dealing with chi-squared, so it might be more accurate to draw something like that. It's not normally distributed. It's skewed right. So, anyways, it's so we want a 95% confidence interval. So the left tail would be 0.025, right? We want to separate the two tails into equally, left and right tails, and we have to divide that the complement 95% by 2. So that would be 5% divided by 2, 0.025, 0.025. So what we're calculating is chi-squared of subscript here would be 0.975, because the area to the right of this chi-squared value is 1 minus this, because this is the area to the left. And this would be chi-squared of 0.025, because that's the area to the right. Okay. Now, the other piece of information, similar to a t-distribution, is we need to know the degrees of freedom. And it is mentioned in the problem that n, the sample size, is 10. So degrees of freedom is equal to 9. So we are looking at the row 9. So flipping to a chi-square distribution, which should be in the back of your book. This is table 7, I believe. And so we can see that we are looking at row 9 for degrees of freedom of 9, and we want to look up 0.975. That would be 2.7. And then we want to look up chi-squared, subscript 0.025 degrees of freedom of 9, and that would be 19.023. All right, there we go. We have our two chi-squared values. Now we're going to use this to determine our confidence interval for sigma squared. And remember that equation that we mentioned? is sigma equals the square root of n minus 1 s squared over chi squared. Now we have two different chi-squares. Now if you think about it, you can think about this logically and think about if you divide by a chi-squared, or if you divide by a smaller number, that will make your sigma larger, right? So the upper bound is actually derived with this 2.7. So, excuse me. So what we would actually do is we would determine our confidence interval using sigma. We're building a confidence interval for sigma of this equation n minus 1 s squared divided by chi squared of, as we mentioned, dividing by a smaller number will make this larger. So we want the upper bound to be larger than the lower bound of our interval, which makes sense. So we would put 0.975 here. Okay. And the 0.025 chi squared would go on this side. So we'd have square root of n minus 1 s squared divide chi squared of 0.025. So this builds our confidence interval equation, and you can remember this in general. So in general, this would be 1 minus alpha over 2, as you can see. Or sorry, no, this is just alpha over 2. As you can see, alpha is equal to 0.05, since this is equal to 1 minus alpha times 100%, remember? And so alpha in this case is 0.05, and so this would be equal to alpha over 2. And this one would be 1 minus alpha over 2 in general, just to let you know. Hopefully you can understand why I put these in this order, and you'll see in a second. So let's go ahead and build this equation. So we have 9 n minus 1. S squared would be 19.8. And divide by 19.023 is less than alpha is less than the square root of 9, the numerator stays the same, and then we divide by 2.7. So there we go. We built our confidence interval. Now we just need to plug and chug. See what we get. So we have a second. Get out of there. So we have a second square root of 9 times 19.8 divide 19.023 and 3.06 is less than sigma. And now we do the same thing. We put 2.7 on the denominator. And we have 8.124. There we go. And there we go. We have just derived, put 1 there, 3 decimals for both. So we've just derived sigma, the confidence interval for sigma. And hopefully you can see now that dividing by a larger number will make your lower bound. And dividing by a smaller number will get your upper bound. So it can be a little confusing. You have this this confusion here, but it makes sense. So if you have any questions, please let me know. And similarly, we can actually same idea. We can do the test statistic, our hypothesis testing. So I'll just show you this right now. So we're going to go into section 10.4. 10.4 is doing a hypothesis testing for sigma. So it uses the same exact equations. In this case, we are actually our test statistic we use the same sort of logic to do all of our steps of our hypothesis testing. And similarly, if you compare how we do the confidence interval compared to the hypothesis testing between each of the variables, mean, mean, proportion, and standard deviation, it should make sense that we would be using the following test statistic. So the only thing that really changes here is the test statistic and the uses of the chi-square distribution. And we can still do the classical approach and the p-value approach. And so our test statistic is using chi naught squared, defined as the chi-squared distribution. The following. So we use that equation. And sorry, that would be naught, and that's based off the claimed value. So it should make sense that, and this is where you really have to think about what's going on with this equation. Let's say that sigma is the claimed value, and then S is from our sample, and we want to compare how close S is to sigma. So naturally, if we it all depends on if we're doing a left tail, right tail, or two-tail test. If this is larger than the claimed value, then we would expect this to be significant. So if we're doing a right tail test, and if we have a sample standard deviation that is significantly large, like in the rejection region, we would expect chi-squared to be significantly large. Hopefully that makes sense. So it's the same idea where our critical regions and how we determine our critical regions is the same. So so the idea is this is in our failed to reject region. I'm just showing you the two-tail version. This is the failed to reject region of H naught, and this is in the reject region. Okay. So if you think about it, if S is really close to the claimed value, then we would expect to get a value really close to n-1. And I didn't really mention this before, but n-1 is the center of really close to the center of the chi-square distribution. So so we would expect to be in the center in the failed to reject region if this is really close to this. And if this is significantly smaller than this, then we would expect to be in the rejection region on the left side. If this is significantly larger than this, we expect to be in the rejection region on the right side. And similar left tail test, we would only have one reject. Like the left tail test, we would just have this, and all of this would be failed to reject. If we had a right tail test, we would have something like this, and the rejection region would only be on the right side. So it depends on what sort of test you're doing. We'll check out an example really quickly. So I'm actually trying to think of how you can use Excel for that. Yeah. So let's go ahead and look at number 10. Number 10 on section 10.4. It's a question about filling machine. Filling machine. So a machine fills bottles with 64 fluid ounces of liquid. The quality control manager determines that the fill level are normally distributed with the mean 64 ounces and a standard deviation of 0.42 ounces. He has an engineer recalibrate the machine in an attempt to lower the standard deviation. After the recalibration, the quality control manager randomly selects 19 bottles from the line and determines the standard deviation to be 0.38. Is there less variability in the filling machine? Use the alpha equals 0.01 level of significance. So, as you can see, we are doing a hypothesis testing on the population standard deviation. By looking at a sample, we're trying to determine if the standard deviation has decreased. And so what we're doing here, if you pay attention to the wording, is we want the variability to decrease. So we have a left tail test. So first off, let's go ahead and do look at the preliminary checks for a hypothesis testing. And notice that the first check is the, so I'll just write check. Checks. So the sample is obtained using a simple random sampling. And you just have to see if it is mentioned in the problem. It does say the quality control manager randomly selects 19 bottles. So it's mentioned in the problem. It is random. Good. Might want to be a little more wordy in like a paper if you write one, but you know what to say here. The population is normally distributed, and I remember paying attention to this, but it mentions that the population is normally distributed. It's mentioned in the problem. So, good. We have our two checks. We're ready to move on to step 1. So step 1 is our H naught. H naught and H alternative. And what parameter are we trying to determine or estimate? Sigma. Okay. So population parameters always go here. Equality always in the null. And then we want to determine is it a left, right, or two-tailed test. We determine that we want to see if the variability has decreased, less than. And what are we comparing this to? We're comparing this to the old standard deviation. So the standard deviation mentioned before was 0.42. That's what it was. That's the old one. Okay, so that's sigma naught. This is sigma naught. Okay, 0.42. And now we're ready to go to step 2. Step 2 is our level of significance, our alpha, and it is mentioned in the problem that alpha is equal to 0.01. Step 3 is our test statistic. And our test statistic, as mentioned before, is this equation right here. Chi squared sub naught is equal to n minus 1. In this case, n is mentioned in the problem. N is equal to 19. So we would have 18, n minus 1, times s squared. And it's mentioned that s squared, of the sample of 19, the sample standard deviation is 0.38. So we would have 0.38 squared. And then we divide by our claimed value squared. 0.42 squared. Alright, so we'll go ahead and calculate this chi naught squared. This would be equivalent to 18 times 0.38 squared divide 0.42 squared. 14.73, we'll just say. 14.73. So there we go. We have just calculated our test statistic. Now, remember, we're doing a left tail test. So if you want to imagine a picture, I'll just use this. If we're doing a left tail test, we can ignore that. The rejection region is here. So is 14.73 far enough left to reject? So we need to compare this to the critical value. And the critical value, since it's a left tail test, we would want the entire area on the left to be 0.01, since alpha is 0.01. So we would look at the column 0.01 and degrees of freedom of 18 and find our critical value. So we would find 18 row and column. Oh, remember, it's not 0.01, sorry. It would be 0.99 because the chi-squared table gives you the area to the right. So 0.99 is the area to the right, 0.99. So 0.99 and column and 18, that would be 7.015. So our critical value would be chi squared of chi squared of 0.99, the area to the right, and that, or yeah, so that would be equal to, I already forgot, you probably remember because okay, I'll look it up again. A space cadet. All right, 7.015. And since we're doing a left tail test, we can see that, just draw a little picture right here, fresh picture. As you can see, the critical value is 7.015, and the rejection region is over here. That's the rejection. This is the fail to reject. And 14.73 is, since 0 is over here, 14.73 is over here. That's in the fail to reject region. So we have just determined, step 4, that based off this picture, we have just failed to reject H naught. Okay? So think about the picture and think about what region is the rejection region. And as we can see, the test statistic is not located in the rejection region. It's located in the fail to reject region. And this is the boundary. Okay? So step 5, and I'll do it on a separate piece of paper. Step 5 is the conclusion. So step 5. And let's go to the flow chart again. And does the original claim contain equality? That is no, because it's a left tail test. You can see. Based off it being a left tail test, we know it said less than, so there's no condition of equality. And did we reject? No, we failed to reject. So that would be a no. So we're on the bottom option. There is not sufficient sample evidence. Sufficient sample evidence to support the claim. Support the claim that ... and we want the original claim in there. And as you can see, we would just copy and paste where it makes sense. There is not sufficient sample evidence to support the claim that there is less variability in the filling machine. Okay, and we can include at the alpha equals 0.01 level of significance. Okay, there we go. And that would be our conclusion for our hypothesis test. So think about the logic of the flow chart and just make sure that this makes sense, that this would be the conclusion of a hypothesis test. So if someone mentioned, if they ask you, is there less variability in the filling machine, this is the answer you would give based off of our sample. Okay? So please let me know if you have any questions. Now for the p-value approach, it may be kind of hard to calculate a p-value from the chart, the chi-square chart, because the chi-squared table gives you approximate values of in increments of like 0.01, 0.05, and if you want to round to 4 decimal places, the chi-squared table does not really do justice. So I'm going to introduce, you can actually solve for it using Excel. You cannot, I don't believe you can do it with your calculator really quickly. If you can, it would be here. Let me check. I am not seeing it. Actually, you can. There's something called the chi-squared CDF, and chi-squared CDF, it's in the same location as the normal CDF under the distributions, which is right above the vars button. Second vars, you'll get to the distributions, and on a TI-83 plus, it's the option 6, chi-squared, or 7, the chi-squared CDF, and that would give you a, I'm going to guess, let me check really quickly just to make sure. I actually have not used this before, or I just don't remember. You would probably need the, well, you would need a degrees of freedom. Not sure if you put N in. And anyways, if you Google chi-squared CDF on TI-83, it will tell you the syntax for it. I'm not sure if they want N and then your chi-squared value. And then it will return a probability. I'm not really sure. So you may have to look that up. It'd be a good little activity to determine. And let me know if you have any questions in solving this. I'm not really sure if this is the ordering. It may be chi-squared N, and it may give you the area to the left, the area to the right. So CDF, cumulative distribution function, is usually area to the left. So if you're doing a right tail test, you would probably want to do the complement of whatever this gives you. I'm not 100% sure off the top of my head, so I'll have to look that up and get back to you on that. Maybe on the next video, or we can talk about this in the discussion, and I'll probably just email you guys about it. So anyways, and I'm going to go ahead and make a kind of cheat sheet of all the different TI-83 tools that you can use to work on chapters 8 through 10 and 11 and 12 and 13, and I'll just add on to it. And anyways, you can do this on Excel too. It's maybe a little more user friendly to do this on Excel. There's a chi-squared CDF sort of thing on Excel. I guarantee it. So you might want to search around for that. But the idea is you want to be able to have a n value and a chi-squared value and convert that to a p-value. Convert your test statistic to a p-value so you can do the p-value approach, because I guarantee you're going to have homework problems on that where you'll need to calculate a p-value. So let me know if you have any questions, okay?